Let us study the building blocks. So bone graphs is just Lego. You have building blocks and you can assemble different kind of systems, just like a Simscape, because Simscape is maybe it's even based on the bone graphs. I cannot say it for sure, but it's pretty close to the bone graphs. And in the Simscape, we just saw that you can assemble piece system out of just iconic representation. In bone graphs, it's pretty much that's it. Pretty much the same. We have few building blocks. It's active elements, it's passive elements, it is conversion elements and junctions. And now we will take a look at them. First of all, it's sources of flows and efforts. So here I created drawings of arrows and pump, just to see that the power direction of the half arrow is the same, but the location of a stroke is different. So on the left we have the stroke on the left, and for the source of effort, the stroke on the right. If it's on the right, it looks like a pump. It means that effort goes inside, flow goes back as a feedback. For the source of flow goes into the port and effort goes as a feedback. Is it clear? A source of flow. It means that we have the source of, for example, of velocity. For example, if we want to model a step motor, we can use a source of flow, like step motor is the source of constant angular velocity, for example. And we will be feeding a system with angular velocity, and the rest of the system will be generate force that goes back as a reaction force into the shaft of the stepper motor. Source of effort, for example, if we want to model constant force, for example, gravity. Gravity is a constant force, and it gives constant force, mj, to the body, and as the feedback, we can measure the velocity of the body that falls. It will be flow. Okay? It's bidirectional flow. Always bidirectional. You know, for example, when we do interaction, for example, I am a robot and I do interact with the environment, the motion is shaped by my motion and the in the environment. It depends on the environment. When you shake your friend's hand, the motion is shaped by the motion of your hand and the hand of your colleague. Or, I don't know, when you shooting a rifle, you have a coil. Due to the you have a reaction. It's always bidirectional, because block diagram, it's not about physics. It's about just assembling an equation, and you can create an equation about everything. You can make bullshit, you know. You can do whatever you like, and it will have nothing to do with reality. This thing about physics, it's about deriving an equation that makes sense due to the physics law. Is it clear now? Okay. We'll have examples. It will be easier to understand. C element. C element is something that stores energy. For example, spring. C is like compliance. Or capacitor. C capacitor in an electric. Store energy. And we have here two types of causality. So here the idea is the following, that if you have an effort as an input, you can calculate flow, but in this case you need to take a time derivative of this effort. Or you can do another way around. You can feed your system with the flow, with the velocity. For for a spring, for example, you can integrate. In this case, you will have the deflection. You can take the energy of a spring, and you can take a partial derivative in respect of generalized coordinate, and you will have the force which generates a spring. And integral causality is greater. It is much more physically consistent. Why? Because in order to take a derivative, you need to know a future state. So here you can see the definition of derivatives. It is a limit, and in order to calculate it, you need to know state. So t, it is the present time, plus delta t. So you need to know future state minus past state. But you're not able to know the future, but you only can predict. So it's estimation. Estimation can be wrong. And in order to make more physically consistent system, which is be more precise, we need to use integral causality. So when we want to create a spring, for example, we want to create a model of spring and damper system. What do we have? We have a source of effort, right? We have gravity. Source of effort, it means that effort goes into the system. Where should I put a causality stroke? Left or right? Right, sure. Also, we have mass, spring, and damper. So spring, I will make it like this. We have a spring, and the gravity is the only reason why the system is moving. So the force will go from the source. So here will be another element that I didn't explain to you yet. So I won't draw anything here right now. But here will be power. Where should I put this causality stroke if I want to be physically consistent? Right here, to have an integral causality. Can you see now? Okay. I can do derivative causality, but it will be not physically consistent. So priority is to use this kind of causality. And we can use C element to model capacitors, springs, and those kind of elements in hydraulics. And this is the equation. For example, force in translation motion equal to 1 over c when c is a compliance. So 1 over c is the coefficient of stiffness times integral of velocity, and the integral of velocity is the displacement x, right? Rotational, pretty much the same. Electric, voltage equal to the 1 over c. C is coefficient of capacitor. Integral of current, it is charge right here. See? It's pretty general. It is true for any kind of physical domain. Another element of building blocks is the I element. We can model mass as I element. So let me do the following. Here will be I element, and the power goes here. And here also we have an integral causality and derivative causality. In integral causality, we feed into the system effort. For example, it will be force. If we take an integral of force, what we'll have? Force, ma, integral of ma. momentum, mv, yeah, momentum, and then we, so this is the integral of force, it will be momentum, and if you divide with coefficient of I, so here it will be the mass, mv divided by m will be equal to the v, flow equals to the velocity. It is correct. Derivative causality, it is when you fit with the v with the velocity, and you take a derivative of your velocity. So it will be, so here actually it's m, I it's coefficient of your element, so it will be mass m, and derivative of velocity, it will be x double dot, so it will be the acceleration. So you still can do this, but as we just discussed the causality, it means that you need to take the future state. It could be not physically consistent. Let us be. L? It's I. I means inertia or inductance, but it's just element I. It's letter I.
Okay, but I element and C element, the same storage energy.
It's store energy, yeah. It's store energy, but different kind of energy. C energy, for example, in mechanics, it's able to store potential energy in the spring. I element store kinetic energy of a body.
It's like in a electrical capacitor and
Sure, yeah. E element, where should I put a causality stroke to be physically consistent? Down, up or down? Down, right. Close to the letter. And finally, I have so here you can see the list of equations for different kind of domains. And finally, we have R element. It do not have causality or derivative, integral derivative causality. It only depends on what you have. And here you can see that flow equals to 1 over R times effort. For example, do you remember the Ohm's law? Can you say the Ohm's law? Okay, so even if you do not remember the Ohm's law, the notation, you can always remember this law and the fact that voltage is effort and current is flow, right? Effort equals to RF. Ohm's law, it is voltage equal to resistor times current. But for the damping force, we also know that force, which is effort, equals to damping coefficient times velocity. The same fact. Flow, yeah, it's a velocity, flow. So, and here we can put the, so it is the direction of power, and since there is no physically consistent relation, we cannot put causality stroke right now. But we will do it in a second. So here for the electrical rotation and for hydraulic also. All right. More than that, we have elements such as a transformer. A transformer, it's something that multiply or scale your efforts or flows. For example, you can think about lever, gearbox, and everything which is indicated here. And I suggest let us have a little practice, maybe for 5 minutes. The challenge is the following. Your task is to think a little bit about those systems, come here and explain us that those are systems actually transformers, and the equations that you can see there is true for these systems. Maybe it's the wrong examples. Did you understand the task? For example, gearbox. What will be the K? What it is? It may be the ratio. You need to come here and prove it. All right? So another one is a gyrator. For example, a DC motor could be modeled as a gyrator. Look, here is a generator, but I will rewrite it as a DC motor. So here as an input we have a voltage and current. As an output we have torque and angular velocity. And due to the equation here, what do I have? That effort here, torque, equal to the some coefficient times not effort but the flow. It depends on current. And we know in robotics that current is proportional to torque. And the same is true for the velocity and the voltage, yes, that they also proportional. And for the velocity, F2, we can write that angular velocity equal to the 1 over k times voltage. Do you agree? DC motor, K is a mechanical constant.
I give DC motor inductance and I need to get
You have a DC motor, you have a battery, you put it here, and your shaft is moving with a constant speed. If you lower the voltage, the velocity also will be lower because it's proportional. Okay. And the final thing that we need to cover are junctions. It's like if we have in the node all forces are the same, or all voltage are the same. In this case, we need to sum all velocities or all currents, and the sum of the currents will be equal to 0. This one is called zero junction, and one junction, it's like when we have the same current in a node, and we need to sum all the voltages to the 0. Does it ring the bell? Does it look?
About the spring mass damper system, we have the same force in the middle.
We have actually for this system we have the same velocity and we need to sum forces. So for the mass spring damper, we had source of effort, we had mass, we had compliance, and we have had a resistor. And here we need to put 1. And the equation of motion will be the sum of all forces which are generated in the elements. Okay? In order to be physically consistent, here as the input we have velocity. So we will be sending the flow as the input, and for the C it will be like this, and for the effort, for the resistor it will be like this, but for the E element we need to send there the force.
I have a question. If it will be 0, it mean like the system will not be transfer the energy from.
No. It's about the node. It's like the sum of all these forces equal to 0. Particularly in this example, it will be the following. Force here goes in, force those forces goes out. It will be E1 equal to E2 plus E3 plus E4.
But can I submission some efforts in another different systems? So we able to add many efforts from many systems in different systems?
Yes, so here you can see it's like different systems and they interact between each other, and the one junction is used in order to describe the interaction. It's very simple system, it's the simplest system, but still it's one of the way how can we describe it. I will show you examples of more complex system.
For example, we would have 0 node or 0. If we are, for example, modeling an electrical system and we are summing a node on the node sigma I equals 0, for example.
Regarding the electrical system, do you remember Kirchhoff's law? The current law, it's all about that in the node we need to sum the current. So it will be which kind of junction? 0. And the voltage law, it will be 1. The Kirchhoff's law is like an example of 0 on 1 junction, but 0 on 1 junction also is used in mechanics. It's more general, yeah.